All right, so I'll make a quick video on optimization. So on your own piece of paper, on a clean piece of paper, just tile that LTF quadratic optimization. And you can find this handout on Canvas. So let me scroll down here. You can skip 1 through 5. I want you to actually go to number 6. Okay, we're going to start there. So our town elementary school wants to fence a rectangular playground for the students. The school can afford 300 feet of fencing material. The playground will be built adjacent. So remember, that means next to. So adjacent to one side of the building. It's only 3 sides require fencing. Calculate the largest possible area of the playground and state the dimensions that give this area. So we have a building here. I'll just make it a simple rectangle here. So we just have our school. All right, and we're going to build this fencing where the school, one side of the school serves as a way to block it in, to create that playground area that we're talking about. So in a different color here, let me show that fencing is everything in red is representative of our fencing. So right here it says that we have 300 feet of fencing material. So let me go back. Most people, when I do these problems, use L, so I'm just going to do the same thing that I've always seen people using. Talking about other students I've had, so they would call that L, which means this is also L at the top. And people just call that the width. You can use whatever variables you want, but I'm just doing the most common ones, like I said. So that part represents our fencing. So 2 L's and the W, because this part over here on the left in blue, remember, we don't have to fence that part because the school building serves as the enclosure part. That's one side of our playground. Okay, so what we're trying to do is, we go back to the question prompt here. So calculate the largest possible area of that playground and then state the dimensions that would give us this area. So I'm going to write the area formula. So our area would be length times width. And what we want to do is determine what's the maximum area we could have, the highest area we can have. But we can't do anything initially because we have an L and a W. We have 2 variables in our area formula. But we know that if we take 2L plus W, right, that was the part that's in red, our fencing, that is 300 feet of fencing. What we can do is we can take this 2L and subtract it over to the other side. So now we have the width in terms of our length, and we can substitute, right, this part right here, this width equals 300 minus 2L, in place of W in our area equation. So now, if we do that, our area would be length times 300 minus 2L. Now, most of you probably like it to be written as the L, right, our length distributed in. So negative 2L squared, we'll write that first, plus 300L. So if I was to say what's the maximum area, well, that would be the vertex of our quadratic, of our parabola. So we would then say, let's find the x-coordinate of our vertex, which in this case is our L. So we would say that L, it would be negative B over 2 times A. So it would be negative 300 over 2 times negative 2, which would be 75, and our units, no problem, were feet, so it would be 75 feet. So there's our first dimension that we're solving for. So our length is 75 feet, but we already had this equation up here, right? Our width is 300 minus 2L, so if we want to find the width, our width would be 300 minus 2 times that 75. So our width would be 150 feet. All right. So now we have our dimensions. Okay, and the other thing it said was we need to find the maximum area. So we can take our 75, just like we do with the vertex of a parabola, and we can take that 75 and plug it back into our area equation over here. And we can do it that way, or we know it's a rectangle. You go back up there and just visually see it again. So we could just say, what's length times width? All right, so our maximum area would be 75, right, times that 150. So 75 times 150 is 11,250. We were talking about feet right here, so it'd be feet squared. We'll put feet in there, you're more than welcome to. So there's our maximum area. Okay, so number 7 now. Kristen needs to enclose a rectangular pen for her cows. She only has 800 feet of fencing. So she will use the 60-foot side, okay, so 60-foot side as part of one side of the fence. Calculate the largest possible area and the dimensions like we did earlier. This is very similar to the problem we just did. All right, so we have I think it's a barn. It's right here. And it tells us that that barn has 60 feet right here. Right? It's a 60-foot side of the barn. But when we make our pen is actually going to be only part of that side. So we can't cover, the barn does not cover all of it. We have a leftover portion. And there's different ways you can draw that picture, but I think this is probably the best way. As far as rather than putting the barn anywhere on that side, I'd probably just put it at the end. And then this is very similar to what we did earlier. This would be our length. And there's two approaches here. Some people actually call this the width. So if that's our width, and this little piece left over here would be our width minus the 60 feet that the barn captures. Now some people will actually go all the way around. They'll just call this some variable length. So we'll call it x. Well, if that's x, and this entire length over here is x plus 60. Either way works. It's going to give you the same answer. It's just what we're labeling as a variable. But just kind of go back to our original one, which is the one that's most common. People will call this a width, which means with the leftover parts, width minus 60. And so obviously from here, it's a very similar approach to we did our last problem. You're going to add those links, the two L's. You're going to add the W and the W minus 60. We don't need to add this part of the barn. We don't need that part because we're not putting that as our fence. It's only the part in red. And now it's going to be equal to 800. And you can go about the exact same process that you did earlier, and I'll let you finish that problem out. All right, so our final problem, number 8. This is the one that I'm actually more concerned with, or problems of this type. So we have, a rectangle bounded by our x-axis, y-axis, and we have our line, P. Okay, it's given a diagram for us. So the first thing it says is write a formula for the base of the rectangle in terms of x. So I'm just going to say the base is B. Okay, so we want to have our final result be in terms of x. So over here, I'm going to make this point a little larger. This point on our line is represented by x comma y right now. So our base would be the distance from the origin all the way to that point. Well, that would be the x-coordinate of that point. So if we're talking about what our base is in terms of x, it would just be x, the x-coordinate of that point. Okay, so part B, write a formula for the height of the rectangle in terms of x. Okay, so our height, this is the part where people kind of get hung up sometimes. The height of a rectangle, I'm going to highlight it, it's right here in red. It's even indicated on our diagram. Well, that would be the y-coordinate. Right? That'd be our y for our point, our given point. So we could just say, hey, our height is equal to y. Here's the only issue, though. It says write that formula for the height in terms of x. So we can't say h equals y. We need h equal something where x is involved. All right, so if we go back here, and I think some people interpret it more like this. I could call this x comma f of x. Sometimes that spurs people to think the right thing here. We want to write that in terms of x. Well, our base can be changing. All right, we can have rectangles that are all different types of base lengths. Right? Our base right now is like at this spot. But what if it went all the way here to 30? So our base was from here all the way to 30. Then we'd have this skinny rectangle. So our base length changes depending upon what it is we choose. Well, our height also changes. But the height is always a point, no matter what, whatever our base is. If it was this one, if it was this one, it's always a point on that line. And that point on that line is dictated by an x and a y value. Well, our y is simply the equation of that line. All right, so if I look at this line, it's x comma y. I'm going to erase it and fix that. All right, so if we're trying to find the equation of a line, first thing to do is to look at the slope. We're going down 20, and then to the right 40. So our slope would be negative 20 over 40, or negative 1/2. And then the point we're given right here, right, 0 comma 20 is our y-intercept. So we can easily write that equation. Our slope, our y rather, is equal to negative 1/2 x plus 20. So that's the equation of that line, which is also the y value, right? Our y value changes depending upon what the x is. So this negative 1/2 x plus 20 is what goes in right in that spot for our point. Well, that is also our height. So our height would be equal to negative 1/2 x plus 20. So now we have our base and our height in terms of x. So part C, write a function for the area of the rectangle. Well, it'll just be base times height. So the area in terms of x, our base is x. We found that in part A. And our height, which we found in part B, is negative 1/2 x plus 20. Part D, what base and height should the rectangle have in order to produce a rectangle with the maximum area, and then determine this area? So you would just take that formula we found in part C to try and maximize the area. You probably like to distribute that x, so I'm going to do that. Negative 1/2 x squared plus 20x. And now, just like we've done before, we're looking to find the vertex of our parabola and then figure out what our maximum area would be when that given x is once we found it. So I'll let you finish that problem out. So all I want you to do as far as homework, if we did number 6 together, finish out number 7, finish out number 8, and then go to the next page. And you should see area and volume applications, and there's 5 problems. You can see we have a rectangles on a coordinate plane for part number 1. Number 2 is right here, another rectangle with some different dimensions and volume and stuff like that. Number 3, and then on the back is number 4 and number 5. So there's those 5 problems. That's actually the homework assignment. It's just getting those completed. And obviously I can answer questions when I return, but we will pick up there when I see you guys next class. And we're going to have a lot of time in class to kind of work on these and understand exactly what's going on, answer questions obviously if you have them. But you guys have a great one. Stay out of trees.